In video 9, I discussed that irrational numbers cannot be expressed as a Cauchy sequence. However, current mathematics present examples of irrational numbers as a limit of Cauchy sequence, which would validate the concept of convergence, limit, and Cauchy completeness. However, I show that the proof is flawed as a circular logic. I will start with an example of square root 2 claiming as a limit of a Cauchy sequence. The proof is as follows. Define a sequence of rational numbers as follows. X sub 0 equals 1, x sub n plus 1 equals 1 over 2 x sub n plus 1 over x sub n. This sequence converges to some real number x. Thus, we have limit x sub n plus 1 equals x, which is equal to limit 1 over 2 x sub n plus 1 over x sub n, which is equal to 1 over 2x plus 1 over x, which leads to 1 over 2x equals 1 over x. And then we have x equals square root 2. And thus, square root 2, which is an irrational number, is a limit of a sequence of rational numbers, limit x sub n plus 1. And it appears to validate that an irrational numbers can be a limit of a Cauchy sequence of rational numbers. However, this proof is flawed, and there is a circular logic in the proof. The proof begins with a statement. This sequence converges to some real number x and writes limit x sub n plus 1 equals x, which is to say this sequence converges to become some unique single real number x. However, the limit of a converging sequence is not unique. Converging sequence does not become a single unique number. Of course, the definition of a converging sequence or Cauchy sequence is that x sub n approaches x as n approaches infinity, which is written as limit x sub n approaches x. However, even though it has been claimed that limit x sub n equals x based on the proposition that the limit of a converging sequence is unique, the proposition is flawed, as discussed in video 1, 2, 3, 3a, 3b, and 3c. Limit x sub n approaches x, but is not equal to x. It is only close to x. In video 3, I discussed an example of Cantor set as a converging sequence, which shows that there are more than finitely many numbers even at its limit. In video 3D, I discussed Dedekind cut. Even though an irrational number r is related to only one a and b, which is the Dedekind cut of that irrational number, a and b should be related to more than one irrational numbers in order for the number line to be continuous. This has the same implication that the limit of a converging sequence is not unique. Thus, the proof is flawed because Cauchy sequence does not converge to become some unique real number x. This flawed assumption that Cauchy sequence converges to become some unique real number x gave the desired result and false assurance in the concept of convergence, limit, and Cauchy completeness as a circular logic. Instead, what we have is this. This sequence converges to some real number x. Thus we have limit x sub n plus 1 is close to x, which is equal to limit 1 over 2 x sub n plus 1 over x sub n, which is close to 1 over 2x plus 1 over x. Thus, we have x is close to square root 2. Thus, x is close to square root 2. Again, x is close to limit x sub n plus 1. Thus, square root 2 is only close to limit x sub n plus 1. Another example of irrational number as a limit of a converging sequence is golden ratio. The golden ratio phi is if a plus b is to a as a is to b, as in figure from Wiki. Then phi equals 1 plus square root 5 over 2. The proof of phi as a limit of a Cauchy sequence is as follows. Let a sequence f sub 0 equals 0, f sub 1 equals 1, and f sub n plus 1 equals f sub n plus f sub n minus 1. Then we can have a sequence f sub n plus 1 over f sub n, which is equal to 1 plus f sub n minus 1 over f sub n. If limit f sub n plus 1 over f sub n equals x, then limit f n minus 1 over f sub n equals 1 over x. Then x equals 1 plus 1 over x. Then x equals limit f n plus 1 over f sub n equals 1 plus square root 5 over 2, which is equal to phi. Thus, it appears to prove that phi, which is an irrational number, is a limit of a converging sequence. However, in the proof, there is an assumption that limit f sub n plus 1 over f sub n equals x. Under this assumption, limit f sub n plus 1 over f sub n is equal to 1 plus square root 5 over 2. However, the sequence converges to, but does not become the unique real number x, which is converged to, as discussed before. Thus, this proof is flawed as a circular logic. Instead, limit f sub n plus 1 over f sub n is close to, but not equal to phi, because limit f sub n plus 1 over f sub n is close to x, and limit f sub n minus 1 over f sub n is close to 1 over x. Thus, what we have is x is close to 1 plus square root 5 over 2, which is phi. Thus, what we have is limit f sub n plus 1 over f sub n is close to phi is not equal to phi. I repeat, the proof of examples of irrational numbers as a limit of a sequence is flawed, because limit x sub n approaches x but is not equal to x. It is only close to x. In video 10a, I mentioned that Cantor wrote the proof of dimension paradox originally in decimal forms, but later in continued fraction to answer the comment by Dedekind. Numbers can be expressed in continued fraction of natural numbers a sub I and b sub I. When a sub I is finite, or any a sub I is 0, it is a rational number. If a sub I and b sub I are positive integers, with a sub k is not larger than b sub k for all sufficiently large k, it converges to an irrational number. For example, square root 2 equals 1 plus 1 over 1 plus square root 2, which is equal to this, and then go on like this. And consider a sequence C sub n like this. This sequence converges. And the question is, will the limit of a sequence C sub n be equal to square root 2? No, it is not equal to square root 2. It will be only close to square root 2, because the limit of a sequence x sub n is close to x and is not equal to x, as discussed before. Another example, phi equals 1 plus 1 over phi, thus is this, and can go on like this. And consider a sequence phi sub n like this. The sequence converges, but the limit of the sequence is not equal to phi, is close to phi. Again, because limit of a sequence is close to x and is not equal to x. It is no wonder that the limit of continued fraction is not irrational numbers, because continued fraction is just a special form of rational numbers. You can examine the difference between phi and the sequence phi sub n. Even though they may look similar, they can never be the same. Thus, Cantor's proof of dimension paradox in continued fraction is flawed, because irrational numbers cannot be expressed in continued fraction of natural numbers. Thus, delusion in the concept of convergence and limit led to delusion in Cauchy completeness, which led to delusion in invariance of dimension, which is dimension paradox. This was so counterintuitive that Cantor himself remarked, "I see it, but I don't believe it," in his letter to Dedekind. But there was no need for this surprise. It was all delusion that began with delusion in the concept of convergence and limit. Professor Gouveia advises, "A proof is not a proof until some reader, preferably a competent one, says it is. Until then, we may see, but we should not believe," as the last sentence of his paper was Cantor surprised. I take his advice to the heart and want you to examine my discussion critically. Therefore, I am inviting mathematicians to fight back my challenge that these three pillars of current mathematics are all flawed, rather than shy away and hide in their echo chamber. Please send critical comments to this address and I'll answer them in this channel. Thank you very much.